not far from being done. We're on the 11th today, so we have all week next week before Thanksgiving break. And on today or Monday, we'll wrap up chapter 8, which is on this whole rotation bit with angular forces, torques, that is, and we'll do momentum and energy and a couple other things. So we'll wrap that up today or Monday, and then we'll spend some time on chapter 9. We're really, for chapter 9, there's no new content necessarily. We're just looking at equilibrium situations, static situations, where the sum of the torques and the sum of the forces is equal to 0. We've already worked some very simple problems with that, but we'll just work through a few example problems, and I'll show you some of the techniques by which to approach those. And then that chapter entirely will be take-home, and I'll give you that take-home next week. It won't be due right after the break. It'll be due when we take the exam. And then the exam is the 5th of December. Normally after Thanksgiving, we just come back and we have 1 or 2 days until the end of the semester. But this year, our Thanksgiving is early, so we have about a week and a half afterwards. So in this week, we will cover optics. That's sort of a departure from this class. Usually optics comes in the second semester, but Dr. Balaji wanted to cover it for you geomatics folks because we no longer actually use, we sort of stopped covering it in the 200 level, but now we brought it back for you guys, folks. All right? So we're almost done. I think you'll find that optics, not a whole, it's not a, they're really just some rules, some simple rules to follow, and I think you'll find optics to be a little easier than chapter 8. And then we'll be done. All right. The final is cumulative. The final is on the 14th of December. It's a late final, and it will come from the 4 exams. So if you want to start preparing for the final right now, hey, why not? It's not that far away. You can just start working through our 4 exams, not old exams from previous semesters, but you might find those a useful tool in the sense that you can find problems that are similar to the problems that we have on our exams. So for extra practice, you can look at those. But if there's material that's not on our exams from this semester, it won't be on the final. That doesn't mean that they'll be exactly like our exams. They'll be similar but different. So I'll change the numbers in some cases. Sometimes I'll sort of change the makeup of the problem a little bit, but you'll still be able to identify it. So if there's a topic on our 4 exams, it's possibly on the final. And the final will be about 1.5 times a regular exam length. You have 2 hours, 1.5 to twice as long. Alrighty, let's pick up with where we were. Remember we did this thing where we derived the moment of inertia. And the way that we did this was that we took a body and then we asked ourselves, how can I break this body up into little pieces? And with the rod, the thin rod, what we did is we just broke it. It was of uniform length. We just broke it into little pieces along the length of the rod. And then we integrated over all those pieces. With the cylinder, you can do that, but it gets pretty complicated to break it into little pieces like that. So instead, because it's circularly symmetric, we break it, instead of into little pieces, we break it into annular cylinders, into little toilet paper rolls. And then we integrate over those cylinders, those hollow cylinders. When you're dealing with this, when y'all go into Calc 3, Chem majors do go to Calc 3, is that correct? And I think engineering majors too. Is that right? Engineering majors, Calc 3, and differential equations? Yeah, so you'll see that when you get into this in Calc 3, that there are different methods to deal with different kinds of shapes. So for example, what would you do you think, if you wanted to find the moment of inertia of a sphere? How would you break that thing up into pieces? What would be your differential element for a sphere? Now with the rod, we just took little pieces and we integrated over that. With the solid cylinder, we integrated over annular cylinders. What would you think you'd integrate over for a solid sphere? Annular spheres, or we would call those really hollow spheres, right? But you're right, you would integrate over hollow spheres. So you take a hollow sphere down in the middle, and then you integrate outward in order to find the moment of inertia of that sphere. Now, I give you the table here that has moments of inertia for various rigid bodies. So here's our hoop, and here's our cylinder of radius r, and here's the rod. These 3 we did. And then here are our spheres down at the bottom. We're not going to go through that derivation, But if you're interested, you can find it online, the solid sphere and then the hollow sphere. For the hollow sphere, you treat this, you calculate its moments of inertia, and then you can use that result for a solid sphere to treat that, to integrate over those hollow spheres. Um, you will have a small take-home portion for this. I'll send it out soon. I think it's probably going to be the rod, but across a different axis. So you'll follow a similar procedure as what we had for the rod before, and then it'll be tweaked slightly. So you have to change your axis of rotation. Probably that's what it's going to be, but I'll send it out over email. All right. I want you to notice a couple of things here that these have differing moments of inertia. Particularly, I want you to look at this. This is our cylinder of radius r, and the axis of rotation is down through the middle. So if you think of me as a cylinder, I can rotate about this axis. And my moments of inertia would be 1/2 mr squared. That's what we derived last time. But notice here, I have the same cylinder of radius r and length d, and the axis of rotation is through the center. So this would be like me doing a front flip, right? We talked about this before, I think, about how your moments of inertia is a lot different depending upon your axis of rotation. And we can see that here, that I have this extra little segment here. We find that the moment of inertia of this cylinder is actually quite a bit bigger than the moment of inertia of this cylinder, depending how long it is. Also notice that the moment of inertia of this cylinder, what is missing from this expression? I have 1/2 mr squared. This cylinder, what does not affect its moment of inertia? The length is not affected. So when we encounter some problems, we'll work through some problems where we have like a flywheel or a disc. Flywheel is just a big flat disc. We're going to use this expression for that because it doesn't matter if it's really long or if it's really small, that you still have the same moment of inertia. All right? Here I have two objects. This is a hoop, and then this is a disc or a cylinder, and they have the same mass. This one's made out of metal, and this one's made out of wood. Metal's more dense, so all the mass is out at a large radius, whereas this one, the mass is distributed throughout. So I have a hoop, and then this is a cylinder or a disc. If I were to put these in a race, which one do you think would win? So I have here an inclined plane. I'm going to let the two go down the inclined plane and see which one will reach the bottom first. Which one do you think is going to reach the bottom first? Do you think it'll be the wooden one or the metal one? Which one do you think will go faster? The metal one. Why do you think the metal? Okay, well, let's see. And it looks fast too, doesn't it? Like it's black and it's shiny, and the wood doesn't go very fast. So let's see. But you want to think about which one has the bigger moment of inertia, because the one that has more inertia is going to be more difficult to get started. So we want to ask ourselves the question, not which one looks faster. This one does look faster, and that might be the answer. But which one has the bigger moment of inertia? And the one with the bigger moment of inertia will be the one that's slower to start, right? It's like an elephant versus a cheetah. Which one of those goes faster? The cheetah, obviously, right? Because the elephant's so big, it just takes a lot of oomph to get it going. But the cheetah is fairly light and lithe, and it can go a lot faster. All right, so y'all ready to see? Are you ready, Jake? Okay, let's see. Oh, which one won? The wood, the old slow wood. Because the moment of inertia for which of these is a lot bigger? Which one has a bigger moment of inertia? The metal one. By what amount is it bigger? Well, this is our hoop. I is mr squared. This is our cylinder, 1/2 mr squared. They have the same mass and radius. So by what amount is the moment of inertia of this one bigger than this one? By a factor of 2, right? This one's smaller by a factor of a half because I have this extra little 1/2 term in here. So this one has twice the moment of inertia. It's like the elephant, and this one's like the cheetah, right? Okay, so let's imagine that we have two objects that are coming together, and we will encounter two objects that come together as we talk about momentum. But right now, I just want to think about two objects that are spinning together, and I want to think about what is their angular momentum. I have a little clip I want to show you. This is from the toy. You ever seen the toy? Probably not, right? It's like from the... So I have two parts that are acting. If I think about the Wonder Wheel, I have the Wonder Wheel, and then we have Richard Pryor inside of it. Richard Pryor, there's his hands, there's his body, there's his feet. That sort of looks like horns coming. That's his hands right here. Anyway, the point is that we can simulate Richard Pryor. We can sort of estimate that he is like a cylinder. He's kind of cylinder shaped because his body's extended out in this way, and so we can imagine that he's like a cylinder. And now I can I can calculate the moment of inertia of the hoop, and then also the moment of inertia of Richard Pryor as he rotates about this axis through his center point. Now, the moment of inertia of a hoop we've already found is equal to mr squared. And the moment of inertia of a cylinder is, well, we have to be careful with this. You want to go to your table, and I have two expressions here for the moment of inertia of a cylinder. Am I going to use this one, or will I use the bottom one? Top or bottom? I use the bottom because I'm rotating about this axis. So the moment of inertia for the cylinder is a quarter mr squared plus 1/12 mb squared. I need to make some estimations for the various masses and what have you. Let's say that the mass of the hoop it's about 10 kilograms maybe, 20, 30 pounds. And the radius of the hoop, well, this is probably about 1 meter. Because Richard Pryor is about 2 meters tall. So we'll say the radius of the hoop is about 1 meter. And so that gives me 10 kilograms times 1 meter squared, which is 10 kilogram meters squared. And then I can also find the moment of inertia of the cylinder. I have to be a little careful with this to make sure that I get the dimensions correct, because it calls for the mass and the radius, and then it also calls for the length. Just look at your table. With a little bit of practice on that table, you'll be familiar with it. But make sure that sometimes students make mistakes about what is R and what is B. So need to be clear on what that is, and it describes it in the table. So the radius of the cylinder, well, on Richard Pryor, that's from about here to here, from his midpoint out to the edge. And I said that that was about 30 centimeters, or about 0.3 meters. 30 centimeters, that's about that far. That's about your radius. And then I also need to know the length of the cylinder. He's pretty tall, about 2 meters. I think he's over 6 foot tall. He's a pretty tall guy. And then the mass, I said, just to make it easy, it's a little big, but maybe 100 kilograms. Then we can calculate what is the moment of inertia for this guy, and it works out to be 36 kilogram meters squared. Let me double check that. That's a quarter of 100 times 0.3 squared. So it's 25 times 0.3 squared. That's 2.25 plus a 12th plus a 12th of mb squared. So that's 100 times 4, 400. Goodness bless you. I get a 33.3. Yeah, that's equal to 36. All right. Now, to find the total moment of inertia, we add those two up. So anytime I have two bodies that come together, if I want to know the total moment of inertia, I calculate the moment of inertia of one of the bodies, and then the second body, and then I just add the two up. Okay? So in this case, our total moment of inertia is going to be 36 plus 10, which is equal to 46. That's in kilogram meter squared. You're not going to have a separate problem where you have to find the total moment of inertia, but as you'll see when we get into momentum, we're going to have multiple bodies that are interacting, sort of like in collisions, although they're not really colliding, but they're coming together, and we'll have to figure out what is their total moment of inertia. And you'll do it in this way. Not a vector, it's just a scalar quantity. It just adds right up. Okay? Practice a little bit, but once you practice, I think that you'll find it's not that difficult. Okay, let's try this quick test. Now remember, with moments of inertia, we have a couple different scenarios. One is where we have mass particles. These are objects that we just treat as point masses. And in that case, we calculate their moment of inertia as mr squared. We did an example back last time where we have the three masses and we just added up sum of mr squared. And then we also have the moments of inertia of regularly shaped objects, cylinders, spheres, bars, stuff like that. In that case, you have to use that table because the moment of inertia is not as simple as just the mr squared. So let's try this one. You can decide which of these that is. Four balls, each are 1 kilogram. This distance, they're on a square. This distance is 1 meter in length. And they're rotating about the heavy black line, which is the axis of rotation. All right, we're sort of all over the board here on the answer. Why don't you ask your neighbor what they put? Uh, are we dealing with a regularly shaped object or particles of mass? Particles, right? Mass particles. And so I say I is equal to the sum of mr squared. So you'll have four terms since there are four particles. And you know the mass, you know the distance of the particle to the axis of rotation. Be careful, it's not stated in the problem. You have to sort of figure it out a little bit. I'm going to stop in about 10 seconds. Stop at 235. 235. Guess if you're not sure. Okay, let's see. I'm not sure. I'm sure it's either B or D. But it's going to be the sum of mr squared. So this is 1 kilogram. And then this distance is 0.5 meters. So I'm going to have 1 kilogram times 0.5 meters squared. And then I have that 4 times. So I just, instead of adding them all up, I'll just multiply it times 4. 0.5 is a quarter. So 4 times a quarter is D, 1. So D is the right answer here. It's equal to 1 kilogram meter squared. Alrighty? Yeah, Jesse? As a what now? Uh, yeah, you could sort of think of it as a hoop, I guess. Yeah, but the hoop would have to have a radius of, yeah, half a kilogram and 4, or a half a meter and 4 kilograms. Yeah, but only because it's rotating about an axis where all the particles are the same distance from the axis of rotation. Yeah, and so that would be a hoop of sorts, because every point on a hoop is the same distance from the axis of rotation. I never thought of it that way, but yeah, you could think of it that way. And in fact, the equation is the same for the hoop, so it works out the same way. But I would be careful if you ever see a group of particles, think of them instead of as a group of particles, because it only works in this case because they're all the same distance. All right, let's look at Newton's second law. If you recall, so just to remind you, we got all this business going where we have, you've written this down, but I'm going to write it down again. X to theta, V to omega, A to alpha, F to torques, and then M to moment of inertia. And so if you recall, we had Newton's second law, which was F equals ma. This law will also apply in circular motion, since the torque, or excuse me, since the torque is a measure of I'm going to call it this angular force. It's not really exactly correct, but we can sort of think of it as an angular force. And the moment of inertia is the rotational inertia. And you can probably think what Newton's second law is going to look like here. I had F equals ma. What's Newton's second law going to be? That's right. Torque is equal to I alpha. This is on your equation sheet, but the torque is equal to I alpha. This is just like our F equals I ma. These are vector quantities, just like with Newton's second law. Torques in the clockwise direction are considered to be negative, and those in the counterclockwise direction are considered to be positive. Don't forget that. Now we'll work through some various problems. They're not going to be nearly as complex as, say, our 2D problems, because we're not going to work in two dimensions. But we'll work through some similar problems where if I apply a torque, I cause an acceleration, and see how that works out. Let's just work through an example. So let's say that I have this disk, and I just want to know its angular acceleration. The disk, I didn't give you the mass, but you need it. Let's say that the mass of this disk is 1 kilogram, and I want to know what is its angular acceleration. So there are a couple of things you'll need to do here. You'll need to figure out the moment of inertia. So why don't you do that first? Determine the moment of inertia of this disk, which is really just a flat cylinder of mass 1 kilogram and radius 1 meter, and then determine um, what is the net torque. We've done that before too. Remember, to find the net torque, you need to identify the forces that cause torque, identify whether they're positive or negative torque, and then add up the torques that are caused by those forces. So find the moment of inertia, I, find the torque, and then since torque is equal to I times alpha, we can then find the angular acceleration. First find I, then find our net torque, and then we can find our alpha. This is a cylinder rotating about an axis down through the middle. So our moment of inertia is going to be what expression? What is it for the cylinder? Everybody all at once. For the cylinder, what is it? It's the 1/2 mr squared. looking back at your table and finding that I is equal to 1/2 mr squared. And so that's 1/2 of 1 kilogram times 1 meter squared, or it's equal to 0.5 kilogram meter squared. Then we need to figure out our torque. Now on the test, usually the way I do this, or in the past I've done it this way, is instead of giving you forces like this, I give you a force that acts at some angle, and then you have to do your cross product to find your torque. We've done that, so you'll certainly see a cross product, and as you look back at the old test, you'll see problems like this where they have a force that is given in vector notation, acting at a certain point, also given in vector notation. You have to do the cross product to find the net torque. But in this case, we need to identify the positive and negative torques. This one, positive or negative? It's a negative because it's causing this thing to go in the clockwise direction. This force is positive then because it's counterclockwise. So my torque is going to be positive F1 R1 minus F2 R2, and that's equal to 1 times 1 minus 2 times 1 Newton times 1 meter minus 2 newtons times 1 meter, which is equal to negative 1 Newton meters. Remember, the negative just means that it goes clockwise, so it's 1 Newton meter clockwise. And then if we want to find alpha, alpha is going to equal to torque over moments of inertia. That's going to be negative, or I'm just going to write it as 1 Newton meter. I'll write it as negative, divided by 0.5 kilogram meter squared. And that's equal to negative 2 radians per second squared. Because it's negative, that means that it's clockwise. So the angular acceleration is negative 2 radians per second squared, or 2 radians per second squared clockwise. Now further, I could also ask you, what is the position or what is the velocity? If you look back at the old test and in your homework, you'll see problems like that where I ask you the position and or the velocity at particular times. So let's just say, for example, I say, what is theta and omega after t equal 3 seconds? What is theta and omega after t equal 3 seconds? In this case, theta is going to be omega naught t plus 1/2 alpha t squared. Omega naught we'll assume is 0, and so it's going to be 1/2 alpha, which is 2, times 3 seconds squared, which is going to be 9 radians. And then I find omega is alpha times t, and it's going to be negative 2 radians per second squared times 3 seconds, which is going to be 6 radians per second. This is going to be in the clockwise direction. And the 9 radians, too, would be in the clockwise direction. So the 9 radians, well, gosh, how many is that? I forget which quadrant it would be in, but you can figure out which, it goes in the clockwise direction. Okay? So you can see problems like that as well. And we're going to get to the work energy theorem, but I want to go ahead and introduce work here. Recall that work, and by the way, just put a star next to this because this isn't in your homework. We'll see work energy theorem, but I want you to know this as well. And I'll include this equation on your equation sheet, but it's not on there right now. Okay, so work, if you recall, was equal to F dot D. Right? So if I think about work in terms of torques, or so this was the dot product. The dot product takes two vectors that are parallel to one another. That's in contrast to the cross product, which takes two vectors that are perpendicular to one another. So if you can imagine an expression for work done in an angular frame, what would it be? Not F dot D, but what? What's our correlated, our analog to F? Our torque, and to D, which is displacement. Not R, that's good thinking, but theta, right. So remember, if we have x, we convert that to theta. So I can say then that work is equal to torque dot theta. Um, torque and theta are always in the same direction. So I can just simplify this then to say, I can just get rid of the dot product, and I can say that it's torque times theta. We'll never encounter a situation where the torque and the theta are in different directions. You can imagine that if I have a torque acting in one direction, I'm going to cause a displacement in that direction. So we'll never encounter that. But our work then is equal to torque times theta. So let's ask then what work was done by this force, or done by the torque. And the work is equal to torque times theta. Our torque what was our torque? 1 Newton meter. Looking at this value right here. So 1 Newton meter is our torque. And then our theta is 9 radians. And so the work that's done is 9 joules of work. Or you can call it 9 Newton meters. Notice here that the units do work out. Work, I mentioned when we went over work in chapter 5, that work can be in units of Newton meters, but I'll express it in joules. Yeah, Nicole. No, you don't have to have a negative 9. One, you can't, the negative just denotes that it's clockwise, and that doesn't apply here. And besides, I don't have negative work in this sense. Okay? So no. I wouldn't count you wrong if you did have a negative, but no. Okay? So this is not in your homework, but you could see it tacked on to a problem where if you've already found the torque and you know the displacement, I ask you what is the work done. Now there is in your homework the work energy theorem, where if I do work on an object, actually why don't we just take a break and do a few clicker questions before we move on to that. We've done some of these, right? We've done this one. Have we done any of these? No? All right, well, let's take a step back then and look at these. This one asks you to rank these in order from most difficult to least difficult to hold. So you have this meter stick with various masses hanging from it, and I want you to rank it from most difficult to least difficult. What that really means is you're ranking it from the most torque to the least torque. Because whatever torque is caused by this meter stick has to be balanced by your hand. And that means that the one that's giving the most torque is the one that's going to be the hardest to hold. The one that gives the least torque is the easiest to hold. So different masses, 500 grams and 1,000 grams, and they're located at different points. Which one gives the most torque, which one gives the least torque, and in between. Good practice for these questions is to first pick out which is the greatest. And then if you pick out the greatest, you'll be able to get rid of either 2 or 3 options. And then ask yourself which one is the least, and then sort of think about the ones in between. All right, we'll stop at 2 minutes, 5 more seconds. A little bit across the board here, but let's look. Uh, C is the one that has the biggest torque, so that's good. Most of you eliminated B and D. I like these ranking problems. I'm not the only one. A lot of people like them. They're good. They help you to think about different physical quantities. But it's a good strategy to look at what are the ones that are obviously big or obviously small. Now, I know that C is the biggest because I have the biggest force at the biggest moment arm. Right? You might think that D was the biggest because I have these two masses, but notice that D is not listed at all. So C is the biggest. And then let's look at these two, and I want to ask myself, how do these compare? Well, here I have 500 grams at 1 meter, and here I have twice that mass, but at half the distance. So if I double the force but halve the distance, I'm going to have the same torque. Because remember, torque is F times R. So if I make F go up by a factor of 2, R go down by a factor of half, then these two will be the same. And so that leaves me only with E. E is the only one that shows A and B equal to one another. Now you could also look at these quantitatively, like actually calculate the torque, kind of like we did in lab, where I don't really keep the proper units. So this would be a relative torque of 500. That's 500 grams times 1 meter. This would also be 500. 100 grams times, or 1,000 grams times a half a meter. This would be 1,000 grams times 1 meter. And then this one would be 500 plus 250. The 250 comes about because I have 500 grams at half a meter. So then that gives me C, B, and A, and then D, which is, or excuse me, C, D, and then B and A, which is E. Let's try this one. This one's similar, although in this case we have a rod with forces acting at different points with different magnitudes and in different directions. Can you rank the torques for these? Notice your biggest has to be either E or D, so ask yourself which of those is bigger torque, E or is it D? Also notice that one of these torques is 0. This one is 0 because my angle here is 180 and sine of 180 is 0. But notice that C is the last option on all 5. Which one is bigger? Is it D or E? Which one has a bigger torque? E has a bigger torque. You might say, well, gosh, this angle, though, doesn't that cause the torque to be smaller? And it does, but only by a factor of sine of 45. So this torque would be 4 newtons times 1 meter times the sine of 45. And this would be 4 newtons times a half a meter. And so the question is sine of 45 bigger or smaller than a half? Well, sine of 45 is like, what, 0.71 or something. So sine of 45 is bigger. So E is the biggest of all 5 of these. So that gets rid of B, C, and D, just leaving you with 2 options. And we will stop in 5 seconds, 2:35. Okay, good. A is right. Um, so I have torque E, which we said is the biggest. And then notice that A and D, here I have A, 2 newtons at 1 meter, 4 newtons at a half a meter, bigger force at smaller moment arm, so they have the same. And then I could just stop there and say, well, B has to be the next one. B is a small force at a small moment arm, so I get a small torque, but it's bigger than this one, which is 0 torque. All right? So these torque problems, they hinge on where your force is applied, the angle at which your force is applied, and then also the length of the momentum. You ever get it? It hinges on it. Nobody laughed. I thought that was funny. All right, let's try the next one. A rigid body is an equilibrium of which of these? It's actually getting a little bit into chapter 9, but which of these are required for a rigid body to be in equilibrium? That means that it's not accelerating in any way. All right, we'll stop at 35, 35. Folks, need to put your thinking caps on this morning. A rigid body is in equilibrium if the net force is zero. Okay? The net force is zero. That means it's not accelerating in a translational way. It's also in equilibrium. This is also required that our net torque has to be zero. Because if our net torque isn't zero, then that means it's rotating. Now, I can have a situation where my net force is zero, but my net torque is not zero. Like, consider this. I have this object, and I have a force in this direction and a force in that direction. The net force on that object is zero, but the net torque is not zero, and so it's going to rotate. Okay? As I said, in Chapter 9, we'll deal with these. These problems can get very complex because, you know, our buildings and our structures that we build are very complex. And they have lots of forces and lots of different torques that act on them. And in order to build something that's in equilibrium that's not going to fall down, then you have to have a net force and a net torque that's equal to zero. All right, two spheres are made have the same radius and equal masses. One is made of solid aluminum, and then one is made from a hollow shell of gold. Gold is a lot more dense than aluminum, so I can make it such that one is solid, one is hollow, but they have the same mass and radius. Which is going to have the bigger moments of inertia? All right, I'll stop at 50. 50. Okay, good. Why does the gold sphere have a bigger moment of inertia? It's similar to what we had here. Which one had the bigger moments of inertia? All right, this one had a bigger moment of inertia. And why did this one have more inertia? Oh, yeah, technically you're right. The other one had a formula with a half in it. But physically, why does this one have the bigger moment of inertia? All of its mass is on the outside. It's like your figure skaters, if they want to increase their moment of inertia, whoosh, they put their arms out. And that puts more mass out at bigger radii, which gives them a bigger moment of inertia. So here, the one with more mass at a large radius has a bigger moment of inertia. All right, let's think about this. Another ranking problem. I really like these, especially in this chapter. I have T's. They're made from two equal length, equal mass bars that are put together like this. I want you to rank them in order from the biggest to smallest moment of inertia. When you're looking at these, you want to think of, well, which has more mass at larger radii? The one with the most mass at the largest radii will have the biggest moment of inertia. Let's ask you right now, which one, because I have either C or A, which one, C or A, has more mass at a large radius? A, right? C actually has most of its mass, or half of its mass, at no radius at all. So in C, this part doesn't contribute to the moment of inertia at all. So our first one is going to be A, and that'll limit us then to just these three options. Now rank these from biggest moment of inertia to smallest moment of inertia. All right, we'll stop at 150, 150. Okay, let's see. A lot of you put D. Let's take a look. So we've already said that A has to have the biggest one, so I can get rid of these two. Now, um, this is the biggest. Let's imagine what is the smallest. I know it's either D or C because those are the options that are given. So which of these is the smallest moment of inertia? Well, this one I said this bar is completely out because it's at a radius of 0. And that's not the case over here. So I'm going to go ahead and venture out and say that this one has the smallest moment of inertia. And that would be correct because this one has a whole bar out at some radius, and then it also has this extra bar that's hanging out. So uh, C is going to be the smallest, so that just leaves me with D and E. And now I want to ask myself the question, which one has a bigger moment of inertia, B or D? And then I can differentiate between these last two options. So which one has a bigger moment of inertia, B or D? Um, it's going to be D has the bigger moment of inertia. Because over here, I lose this bar completely. And so this one, these two are identical, except for meaning this one and this one are identical if I were to leave this bar out completely. All right? So you see, I would have this bar rotating, this bar rotating. If I left this bar out, those two would be identical systems. But it's not out, so that means this one has the bigger moment of inertia. So I'm left with A, and then D, and then B, and then C. All right, so the answer is D. Yeah, I did well on that. People usually don't do very well on that question. That's good. Yeah, I've been saving this one for y'all for a good. This is a good one. You ready? Did you hear about the stormtrooper that had a Wookiee steak? It was a little chewy. You're gonna be telling your friends that one all day long, aren't you? Everybody you see. That moment of inertia is which of these? We're almost done. Oh no, we have a few more. All right, well, we'll make this our last one, and we'll stop in about 10 seconds at 35. We'll go on to 38. Okay, awesome. A is right. It's the rotational equivalent of mass, right? We had M before, now we have I. It's similar to mass. Well, y'all have a great weekend, I guess. Yeah, good weekend. I'll see you on Monday. We'll finish this chapter and start up chapter 9 on Monday.